Welcome back for 7.2. We're going to be expanding on what we just talked about waves and what we talked about last year and try to make this big picture come clear for this. So we know from last year that the energy that when we burned those elements and we had green fire and red fire and everything like that, we could calculate the energy by the wavelength of light by using Planck's constant times the frequency or times the speed of light over the wavelength. Okay, we did that last year, so let's remind ourselves of this really quickly. With the example we just did in 7.1, let's say that my wavelength is red light and it has a wavelength of let's say purple light, going the opposite end of the spectrum, and it has a wavelength of 450 nanometers. Alright, so Planck's constant, H, is equal to 6.626 e negative 34 joules times seconds. Remember, joules is a unit of energy. So I would go 6.626 e to the negative 34 joule seconds times the speed of light, 2.9979 e to the 8th meters per second. 450, and that's nanometers, so I'm going to change it to meters by e to the negative 9 meters. Check out my units. Meters cancel, seconds cancel, so I'm left with joules, which is a unit of energy, which is I'm great. So joules goes to energy. That's what I want it to do. That's awesome. So for this, I would say that my energy of purple light is 4.41 times 10 to the negative 19 joules. Okay. A second equation that we didn't look at last year is, so the one that we were using is energy is equal to hc over lambda. We now know about frequency, and we can rewrite this energy equal to h nu, which is just that c over lambda. Okay, so if they give you frequency, use this formula. If they give you wavelength, use this formula, and you're all good. Okay. We also talked about last year that each of these is quantized. So in my Bohr model, which we'll talk more about in the next section, but I want to quickly remind you of it here. Remember, you had your first energy level, your second energy level, your third energy level, so on and so forth. And the electron could jump up to here and then fall back down, or it could jump up to here and then fall back down to there, or back down to there. These energy levels are quantized, so they're like stairs. Right? I can step up onto my first step. I cannot step to 1.5 or 1 3/4. Right? The electron can jump up between these energy levels and it can relax back down into these energy levels, but it is exactly at these energy levels. That is quantized. And we will look more at the Bohr model in the next section. But from this idea that energy is quantized and that energy has to do with mass and velocity, Einstein comes up with his E equals mc squared. Okay, which is saying energy is equal to the mass of an object times the speed of light squared. So since I'm squaring the speed of light, which is a big number anyways, anything that I have mass-wise, I can convert back to energy. And it is going to be a huge amount of energy. So you are a huge amount of energy. The mass in your body is huge amount of energy. Or you can take a lot of energy and make just a little bit of matter. Either way works. And when we do an atomic bomb, we actually can prove this theory. Going back to this whole duality idea where we have matter existing as a particle and a wave, Schrodinger's cat thing that we talked about last year. Once Einstein thought about this, and he got all of his equations put together and people were exploring this, they started thinking, well, if an electron is a wave and we're made up of electrons, then we are waves as well. And so they started trying to prove this, and they came up with this formula that the mass, and the proof for this is in your book, the mass of an object is equal to Planck's constant times the wavelength, divided by the wavelength times the speed of light. Okay, if I'm a little bit creative with this, I can flip things around and I can say then the wavelength of anything is equal to Planck's constant divided by the mass of the constant times its velocity. Okay, and this is the speed of light, which is a velocity. So if it's going at the speed of light, we say the speed of light. If it's not going at the speed of light, we slow it down to whatever speed it is going at. And we can show the wave-like nature of anything. So let's do this really quick with an electron and with a softball to see what we get. So the wavelength of an electron is equal to Planck's constant, 6.626 e to the negative 34, divided by the mass of an electron, 9.11 e to the negative 31, so extremely small mass, times the velocity of the electron, which in this case is 1.0 e to the negative, or positive 7. And this problem is coming from page 281. Okay, so we find that the wavelength of an electron, or how often it peaks, right, is once every 7.27 times 10 to the negative 11 meters. Okay, so very, 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 very small wavelength, which you would expect because an electron is very, very, very small. For a softball, again we use Planck's constant. It's a great thing about constants, you don't ever have to think about them. It has a mass of 0.10 kilograms, and it is traveling at a speed of 35 meters per second, which means that we have an overall wavelength of 1.9 times 10 to the negative 34 meters, much smaller than that of the electron. Well, the electron's tiny to begin with, and its wavelength is tiny, but it's slightly bigger than the electron. So the wave-like portion of the electron is huge compared to the electron, and so you have to consider that. Well, with a softball that is, let's say that big, and its wave is times 10 to the negative 34 meters, it's just not big enough to really consider, and it's not big enough to really worry about the wavelength of a mass that is bigger than an electron, really. Even a proton is usually considered too big. It will do some wave-like things, but we only really look at it with electrons.